Hello and welcome. This is the next, well, it's not really a topical video, it's the June 2009 Unit 2, just had to double check the year, it was June 09. Anyway, so this is the situation we're given at the start, okay? So there's this cyclist and he's pedaling down the hill. We're told that he's got an initial velocity of 0, in other words, he's at rest, okay? And he builds up just as he hits the horizontal section of the road of 16 metres per second. We're also told that the mass of him and the bike combined is 68 kilograms. Now they could have been really nasty and just split it up and told us the mass of the bike, and then put in little letters somewhere, in little font somewhere else, the mass of the person. Okay, as well as the bike. But they've given us combined, and you would always take it as a combined answer. Okay, so the first part says calculate the total kinetic energy of the cyclist on reaching the horizontal section of the road. Okay, so we know that the formula for it's a very simple question. Okay, it states that the kinetic. We should know that the kinetic energy is given in your formula sheet anyway. That the kinetic energy is equal to a half mv squared, okay? So the kinetic energy is equal to half mv squared. Now, the velocity is the velocity as soon as he reaches the end of the slope, okay? So just as he gets that horizontal bit, because that is when we are asked to calculate the kinetic energy. Sorry about that, I just had to double check something. Anyway, so as we know, the kinetic energy is a half of mv squared, then the velocity at the bottom of this slope is equal to 16 metres per second. So simply just sub in 16 metres per second into this equation. And obviously the mass is 68 kilograms, so it's very, very easy. So half times 68 times 16, and obviously don't forget the squared. And remember, obviously, because this is a measurement of an energy, that the units will be joules. Now, with every units question, this is because it's an easy question, I think we've gone through it very quickly, so I just want to make some quite, obviously, sorry that I get you 8,704 joules. I just want to make a quick point here. Now, I will make it in other past paper videos as well, that have short questions, but whenever you're not sure of the units of a question. This is more easy in AS physics, but it becomes a bit more of an issue when we start to look at it at A2. Because you know the units of mass quite clearly are kilograms, and you know the units of velocity in meters per second. Granted, meters per second is squared, so you square the units as well. But if you times them together, then you will get kilogram meters per second, which would just be, which is momentum, okay? But as I said, obviously for this it'll be different. Now, I don't want to get it wrong off the top of my head, but you would combine them together to get your units, okay? If you weren't sure, you didn't remember it was joules, okay? So, kind of a backup, but hopefully you remember that. So as I said, it's a very quick point, and I will make it again, so don't be put off by the fact. It's quite a difficult one to do with that question. So, hopefully you just remember it's joules. It's fairly easy to do. Anyway, so the next one, 1A part 2, the height difference between the top of the hill and the point is, I've labelled as 12 metres, and that's what it says. Calculate the loss of gravitational potential energy of the cyclist and his bike. Well, quite clearly, it's going to be very similar to that, okay? But because of the fact that, well, obviously, gravitational potential energy is lost. He's at 0 metres, okay, and he was at 12 metres. Now, ideally, what you do in this situation to calculate the gravitational potential loss is you use the gravitational potential after, take away the gravitational potential after, okay, take away the gravitational potential before. Obviously, that will get you a negative figure, but it's, the other way around. Sorry, it's the gravitational potential before, take away the gravitational potential after. So it's a difference in the gravitational potential energy. Sorry, confusion. It's simply just GPE at its top, okay, because it's at 0 metres, so the end GDP, the new GM, oh, God's sake, shut up, Will. Gravitational potential energy is going to be 0, okay, and he had whatever it was at 12 metres. Okay, so you calculate what it was at 12 metres and that's how much you've lost. So GPE, you should know, is mg times delta H. Okay, and ideally, if no forces were lost to resistance, GPE and its increase in kinetic energy would be exactly the same. But obviously they're not, because we're going to use a rounded figure for G here. So mg, obviously you just put 68 kilograms times 9.8 times delta H of 12 metres, which gets you 8,000 newtons when rounded. Okay, obviously truly comes to be about 7996.8 joules, but you can, sorry, not newtons, joules. Okay, so you can see they're very, very similar. Well, actually that's quite a lot more. Sorry, I do apologise, don't listen to me. Yeah, but I was writing the fact that if they were, and there was no energy lost to resistance forces, then these would be the same. But because they're different, obviously we're going to have to calculate something else later in the question. Probably didn't explain that very well, but anyway. Okay, so that's the first part of the question. 1A part 3. It says the work done. Now this question, I think, is personally quite confusing in the way it's worded. When I did this paper, I wasn't sure exactly what it was asking, so I'll try and help you around it. It says, 1A part 3, the work done by the cyclist when pedalling downhill is 2,400 joules. Account, this is the word bit, account for the difference between the loss of gravitational potential energy and the gain of kinetic energy. So that wording there, account for the difference. So what does that mean? Well, quite clearly, when I think that, it's almost calculating the difference. But because it's saying account and not calculate, you can just state where it's gone, or you can do both. You can do a point of stating what the energy's been lost to, okay, and doing the calculation. Now, if you go online for this, okay, it's got the mark scheme is very, very easy, I think, personally, for AQA AS physics exams, okay, especially this one. Maybe some of the questions aren't so helpful, but this 1A part 3 is fairly helpful. It just lists a few bullet points that you could list, okay? So I do agree the wording is stupid with this question, especially for question 1. I thought maybe it's just me being thick. So the ones that I picked for this, that the energy is wasted due to friction, okay? So that accounts for the difference, or as I said, you can label that after. There's 2 points, I probably should label this up. So 1A part 3. So the first point I made was about that the energy is lost due to friction, so energy lost due to resistance forces such as friction, lost due to overcoming resistance forces is the better word. Okay, and then I did the calculation. Well, we're told that the work done by the cyclist pedalling downhill is 2,400 joules. Okay, but we need to account for the difference between GPE and basically this is the equation, and it will probably make more sense if I write it down. So the energy lost is equal to gravitational potential energy plus work done take the kinetic energy, and that's always the case in terms of gravity. Because the reason why that is, well, gravity is the energy we had take away the energy that we've got at the end, okay, and that's the energy lost, okay. The energy we put in at the start, well, gravitational potential energy is obviously what we had at the start, but it's also put in 2,400 joules, so it's not lost 200, it's not ended up with 2,400 joules, he's put it in, okay, so it's not an end energy. So you add the 2 energies at the start, gravitational potential energy and work done. Now, granted, these are not all the work done at once, but because we're putting that in, we assume we're putting that in at the start, okay, think of it like that, and we're coming out with the kinetic energy. He's not coming out, still putting the work in. When he's got to the bottom of the slip, that's it, gives up, okay. Not with life, with just recycling. Maybe life when he starts doing it. Anyway, so that's your energy loss. You simply put in the values that you are given. So you get the energy loss to be, the GPE is 8,000 joules, or, I mean, that was a rounded up figure. You may want to actually, it's probably better using your official figure from question AIA, Okay, and you add that to the work done, you take that away from the kinetic energy. So in other words, you 8,000 plus 2,400, take away 8,704, which if you use the correct figures, gets you approximately 1,700 joules when rounded. Okay. Sorry, I get to keep this in my hand because to make sure I was getting the 3 points that I'd put down. Not because it was a bit thick. Maybe that's something else, so another aspect to it. Okay, so a very, very simple explanation to that. But as I said, nothing too challenging. The next part of the question says, the cyclist stops pedalling, okay, so it now turns into a Suvat equation. So hopefully you've got this little bit of information that is towards the bottom of the board, okay. So the next part of the question says, the cyclist stops pedalling on reaching the horizontal section of the road and slows down to a standstill, okay, so it's quite key, bits of information already told you, 160 metres further along this section of the road. Assume the deceleration is uniform, in other words it's the same, it's a constant deceleration, so don't be put off by that word uniform, it just means constant, okay. I know the only other time you see uniform is when you talk about uniform rod, and when we talk about uniform rod, we say the centre of mass. Giving it away there. The mass occurs at the centre. In other words, it has a centre of mass. Okay, but this uniform just means constant, straight. Okay, if you think of a uniform ruler, it's constant, straight. Okay, so anyway, key bits of information. As I said, with all these Suvat equations, and all the equations for that matter, that require calculation, the first thing you always do, and I stress this especially, comes more into Suvat equations, is write down what you've got. Okay, so obviously we know as this 1b part 1. Obviously we know that is this final velocity here is because you can, if you imagine this is stage 1, okay, when he reaches. Stage 1 is when he sets off and he's pedalling down the hill. Stage 2 starts when he hits the horizontal bit. And we know his velocity because of our calculation and what it's told us. What it's told us. His velocity when it reaches the horizontal section is 16 metres per second. So therefore, there's no sudden change in his velocity in infinity. There's no infinity change in his velocity. So therefore, what I'm trying to say is his velocity at the end of the first section is his velocity at the beginning of the second section, because section 1 and 2 happen right after each other. What I'm saying is, because his velocity at the end of the we're told that his final velocity at the end of the slope is 16 metres per second, so we take that as an initial for this part, okay? So therefore, hopefully that made sense. If not, I can probably confuse you. Okay, so his initial velocity is 16 metres per second. We're told he comes to a standstill, which is quite clearly saying he comes to rest. In other words, he comes to 0 metres per second. Okay? A further 160 metres, so his distance to stop is 160 metres. And it wants his time. Now, you could do a variety of equations here, but the only one that I would recommend, because it's the easiest, well, what we've got here is we've got U, we've got V, we've got S, we've got T, okay? So trying to think of if I've done it a more complicated way than needs to be done. Well, let's think about the Suvat equations that we can use here that involve T. Well, we've got V squared equals U squared plus 2AS. Okay, well, that would get us A, but that's not going to get us T straight away. So let's see if there's an equation which can get us T. Okay, so that links all the ones so far. We've obviously got S equals UT plus a half AT squared. Well, again, that's going to, we can't use that because that's got two unknowns. We don't know the acceleration and we don't know time, so you can't use that. We could use this to get the acceleration and then use another equation to get time, but as I said, that's the main two equations. And then obviously we've got the equation S equals a half U plus V times T. And that is the equation that we would use because we assume the deceleration to be constant. It's not asked us for the deceleration, okay? Okay, it simply asked us for the time. So we're going to use that equation, subbing what we know. So it's 160 metres is equal to a half of u plus v, so 16 metres per second plus, sorry, plus 0 times t. Okay. So yeah, this actually works. I do apologise. Sure this is going to work. So therefore it'd be 160 over 8. It's 20. Yeah, it works. I was worried then for a second it wouldn't work. So therefore t is equal to 20 seconds, which is the correct answer. So even though we're decelerating and we've not included that factor, it's not asked for that, so we don't have to supply it, okay? So we get t to be 20 seconds. Now the reason I was kind of looking a bit perplexed there is because I worked it out a different way. In other words, I worked it out a long way, but there's a bit of information in my old working that you need to be able to work out the next part of the question. Okay, so the way that I was going to do it, okay, was use, because we had the final velocity, the initial velocity, and the time, and the distance, okay, I used v squared equals u squared plus 2as to get the acceleration, okay, obviously it'd be a deceleration, and then use v equals u plus at to get t. Now, you get the exact same answer, and if you have any other ways, please do let me know in the comments below, and I'll put it as a little box in this video to help other people. But we do need the acceleration, and I'll explain why, because it occurs in this next part of the question. Okay, so the next part of the question says, calculate the average horizontal force on the cyclist during this time. Okay, well the only force that we know of is in terms of to do with mass and acceleration is F equals ma. Okay, that's the only force. Now it's not going to be mg sine theta or anything, because we're not assuming he's on this section anymore, we're assuming he is on the horizontal section. Okay, so we don't need to take into account for any angles. Okay, so well, we know his mass, but we don't know his acceleration. Now this is going to be a deceleration, but because you may go, oh well, that will give a negative force, and we can't have negative forces. Well, it just means it's in the opposite direction to the way it's going, which is obvious because it's like a braking force, and if the braking force acted in the way you're going, you'd speed up, and it kind of throws the whole thing out the water. So anyway, what we need to do is work out his deceleration. Now, I kind of rubbed all the information off, but it doesn't really matter. The initial speed was 16 metres per second, okay. The final speed was 0 metres per second, and his time is 20 seconds. Okay. We can use, to get the acceleration, deceleration, we can use v equals u plus at, rearrange to get a, so a is equal to the change in velocity, v take q, which is obviously minus 16 metres per second, over 20 seconds, okay, and if you sub that into your calculator, you get an answer of negative 0.8 metres per second squared, okay. And we sub that in to F equals ma to get the force. We're not finished now, okay? So F equals ma, so 68 kilograms times 0.8 metres per second squared. Okay, so it's going to be negative, but it doesn't really matter because we're not because the force is going to be positive. It's just acting in the opposite direction. Okay, so you do 68 times 0.8 metres per second. Okay. And I'm just going to do that on my calculator and just double check something. Okay, so you get 54.4 meters. Okay, and that is your answer. You don't actually do anything else. I'm just trying to think if I've done it. Sorry, I was thinking of something else. So that is what you do. Now the reason that's the average force is, well, it's not good. You might think, oh, we divide it by the distance, okay? But you would only divide it by the distance, as it says on there, if you were working out the loss in kinetic energy, okay? If you hadn't worked out the acceleration. So in other words, what you could do to answer this question is work out the loss in kinetic energy, which is obviously what you worked out in whatever your answer was to 1 part A, I, the first part of 1A, okay, which I think has got to be 8,700 joules. And you divide that by the distance of 160 metres to stop, and you would get your average force. But we didn't divide it by the distance here because, well, our acceleration was, it's not going to be, you know, it's not going to slow down uniformly, even though it says it is. You know, there's going to be small fluctuations in it, okay? Obviously due to resistance, forces, air resistance and whatnot. So the acceleration is kind of, the deceleration that we work out is kind of an average, okay? So that's the average resistance force. Now don't divide that by the distance, okay, on that question. Right? So hopefully that made sense. Sorry about the little confusing bit at the end there. I made a little bit of a mistake thinking I was, because obviously there's two ways to answer this question, and I done both ways in my answers, and I was mixing them together, but that is the right way. I didn't say anything that was incorrect. I was unsure of myself and doubted myself for the first time correctly. You know, normally when I doubt myself, I'm correct. Okay, so even the best of us get it wrong at times. Anyway, so that's it for question 1. Hopefully, we'll see you in question 2. So hopefully, I don't really care. Thanks for watching. Well, obviously I do care, you know. I'm not this kind of guy that doing all the videos for absolutely no reason. As you can tell, it's getting quite late. Anyway, so thanks for watching, and we'll see you in the next video.